Newton's first law. So this is just a hoop with a marble here that I can spin around this way. And what I'm going to do is, what I'm going to do is spin the ball around. Okay, very simple. What happens when when I remove the wall, the ball goes off in a straight line. Okay? That's what things want to do. Why is the ball not going in a straight line when it's in this hoop? Because there's a physical force acting between the wall that's pushing on the ball that's making it change its direction. That change in direction of its motion means it's got an acceleration. So force is acting on it, even though it's going around this hoop at basically a constant velocity. And once I remove that force, it goes in a straight line. And that's going to continue going in a straight line, thanks, until some other force acts on it. In our everyday experience, that other force is friction. Right? So friction tends to slow things down. Okay? So what I want to do next, where did I do this last time? Remember which table I used for this last time? Is illustrate friction. So you did the ball for the demonstration with Andy last week, where she had that massive ball and the strings, and she yank it slow and yank it fast, right? So this is the same principle, but with different material. If I pull slowly on this, what happens? The beaker moves towards me. That's because there's a frictional force between the cloth and the beaker, and that frictional force is strong enough to accelerate the beaker from not moving to moving, and then it moves with me. Okay? If I try to accelerate this beaker very quickly with friction, if the frictional force that I apply is too weak to make this thing move, then it won't move. The frictional force, as we'll see in the upcoming chapter, is proportional to the weight of this object. Okay? So there is only a certain magnitude of the frictional force that can be applied to this beaker by the cloth. If I try to accelerate this thing at 100 meters per second squared, 10 Gs, something like that, if I try to move this thing very quickly, that force that I need is the mass of this beaker times that 100 meters per second squared. It's a very large acceleration. I need a very large force. If friction is not large enough to supply that force, by me giving it a very strong acceleration, then what's going to happen? Okay? It can't come with me. So, if I give it a small acceleration, the frictional force is strong enough to move it. If I try to give this thing a very large acceleration by pulling on the cloth very quickly, the frictional force between this and the beaker is not strong enough to make it accelerate. Okay? So it just goes. It did the same thing with the ball and the string. She pulls it very quickly. The force, the tensile strength of the string was not strong enough to make the thing go. Just talk about toilet paper? No, I'll guess. Same thing with a roll of toilet paper. If you got a big, new roll of toilet paper, you can snap it and you get whatever you need. Because the roll has a lot of inertia, has a lot of mass. That toilet paper roll is down to the end. It's got very little inertia. I can pull it very quickly and fingers can pull like that because there's not enough inertia to stop it. Okay, enough scatological